Okay, this one today, I'm gonna maybe not ask for quite as much input today, just because I'm finding I'm having a hard time getting through all this. Oops, can't hear me. Let me say that again. Uh, I'm going to maybe today not ask for quite as much input as I normally do, just because I'm finding I'm having a tough time getting through this whole thing. And I think once we get going on it, you're going to see that it's really not that big a deal. It's not like it's that complicated, but there's some points I want to make about each of these functions we're going to discuss. So what are we doing today? So today we're going to define a bunch of parent functions. Okay, and the reason we're doing this is because even though we spent a lot of time on probably our biggest section that we ever cover, which is 3.1 over piecewise functions, we spent a lot of time on that, but that's kind of an oddball section in Unit 3. Unit 3 it really ends up being more about making graphs of specific kinds of functions than it does focusing on piecewise functions. And it culminates with, we're going to start exploring the graphs of quadratic functions. And we're going to look at quadratic functions in vertex form at the end of the unit. And that's kind of the whole, our ending point, and that's really the high point of the unit. But along the way, we're going to learn how we can take a variety of really basic graphs that we're going to call parent functions, the most boring, basic kinds of type of graph for a bunch of different functions, and how we could transform those. How could we translate them around, move them around in the XY plane? How could we reflect them? How could we stretch or compress them so they look, taller and skinnier, or shorter and wider? How could we do some things to these graphs to make them a little more different and interesting, starting with these basic parent functions? So just a couple quick definitions. In math, we say that a family of graphs is just a bunch of graphs that are very, very similar. They display similar characteristics. A parent function is the very simplest function of that family. Okay, and we're going to look at some different types of parent functions, like a linear, absolute value. We'll look at quadratic and cubic and some others too. So what we mean by this then, if we look at a linear parent function, and honestly, this is one we could probably skip. I'll just use this as our warm-up. We've done so much work with graphing lines and writing equations of lines that this is probably unnecessary for us to even do this one. But like I say, we'll just do it just to kind of get started here. So our linear parent graph, or parent function, the simplest line that we could draw would be y equals, or we're going to write these in function notation. So f of x equals x, right? If I think about that in y equals mx plus b, slope-intercept form, the slope is 1. There's a 1 in front of the x, and I'm adding 0 to it, right? So b is 0. So we know what this looks like. This is simply going to be a line with a slope of 1 and a y-intercept of 0, right? So it's just a line through the origin with a slope of 1. So that's what our parent graph looks like. Some key points that we might want to have on this thing are 0, 0, because we know it goes through the origin, and then it goes through the point 1, 1, and it goes through the point 2, 2, and 3, 3, because after all, the output is equal to the input. Y is always equal to x. So the stuff we're going to fill out, and I should have mentioned this earlier, you might want to dig out this notes template from your packets. Okay. I'll publish these notes, and these will be published by the end of lunch today. These things will be up and ready to go. So if you can't find it right now, that's okay. You could just fill in the blanks later if you want to. On that packet, there's some other information that they're asking for up in this region. You can just cross all that out. We're not interested really in that. All we're interested in are these parts of the characteristics. The ones that I'm going to go through is it. The other ones you can just forget about and cross out. First one is the domain and the range. We've talked a lot about domain and range. Now think about what the domain means, right? The domain is just the set of all the x values that are included in our graph. Couple other ways to kind of models to use to think about that. If an ant is walking along this infinite function, what are all of the x coordinates the ant could stand on? Well, what are they? Real quick, just in chat, everybody tell me, what's the domain of this? And let's be really quick about this. Let's get it. Everybody needs to answer, but let's be really quick. What's the domain here? Are there any x values the ant couldn't step on if he walked on this? Yeah, it's all reals, isn't it? Right? Negative infinity to positive infinity. Well, we'll just call that all reals. There's no x coordinate the ant couldn't stand on. What about the range? That's the set of all y values. Is there any y coordinate that the ant couldn't stand on? No. He could stand on any y value he wanted to if he went far enough along this function, right? And so that's also all reals. If we think about it in terms of projections, well, we could do that too, right? If I projected this graph onto the x-axis, wouldn't it just cover the entire x-axis if I projected it onto the x-axis? Yeah, it'd be all reals, right? What if I projected it onto the y-axis? Well, it would cover the entire y-axis if I smashed it onto the y-axis, right? And so again, it's all reals. Okay, end behavior. This is a little bit strange. This is something we haven't talked about. We talk about this a lot in calculus. We call it limits in calculus. We don't really have to talk about it in terms of limits here, but it means the same thing. The end behavior is asking us, what is this function doing at its ends? If I go clear out to the right or the left as far as I can, what's the behavior of the function? Well, there's no limit to how far an ant can go to the right or the left on this function, correct? So how would I say that then? As x approaches, if I want to figure out what the end behavior is at the right edge of the function, but there's no limit to how far the ant could go to the right, what do you think I would say here as x approaches what? And by the way, when I say, let me make a note of this here. When I have an arrow like this, that arrow literally means approaches. It means the word approaches. So we'd read this as x approaches what? If I'm going as far as I can to the right, but there's no limit, what would I put there, do you think? Infinity, that's it. Yeah, as x approaches infinity, positive infinity. That means we interpret that to mean as the ant goes to the right forever, we got to fill in the blank here. F of x is just y. What is the output f of x or y approaching? As I go to the right forever, don't I go up forever also? Right? As the ant goes to the right, the graph is taking him up. And so his y value is also going to approach infinity because he's going up forever, right? So what f of x approaches, if it's approaching infinity, it just means it's going up forever, right? That makes sense? Okay, so that's all we're answering when we talk about end behavior. Well, let's look at the other possibility. What if the ant is going as far as possible to the left? So on this graph, the ant could go forever. So as x approaches negative infinity, well, as he goes left forever, doesn't the ant also go down? The function takes him down. So f of x or y would approach what then? As x approaches negative infinity, meaning as I go left forever, y or f of x approaches what? Yeah, also negative infinity. You got it. Okay. Now, what about continuous or discontinuous? I'm going to add a little bit of notes here. Here's how we know. Okay, so I'm just going to type this because this pen is so bad. A function is continuous if I can graph it without ever picking my pen off the board. Come on, there we go. That's our definition of a continuous function. Okay. So you tell me, is this function continuous? Could I graph this entire line without ever picking my pen off the board? Yes or no? Yeah, I see people shaking their heads. Yeah, I could, couldn't I? Right? There's no reason for me to pick my pen off the board. And so the answer is continuous. Okay, that's all we're doing for these functions. Okay, that was a pretty boring one. Let's pick some more exciting ones. Let's pick something like, I'm going to move this down just a little bit. Let's pick something like an absolute value function. So our most basic absolute value function, our parent absolute value function, is just the absolute value of x. Okay. If I want to get the shape of a graph, we've talked about this a little bit. The best way to do it really is with a t-table. So let's make a t-table of just x and y values. X's are my inputs, y is my output, f of x, right? Well, if I input a 0, what's the absolute value of 0? Just type it in chat or somebody say it. What's the absolute value of 0? 0, yeah. Okay, so that tells me I have an input of 0 and an output of 0. So I get a point on the graph at 0, 0. Okay. What about if I input a positive 1, what's the absolute value of positive 1? Wasn't that just 1, right? So I know I've got a point at x equals 1, y equals 1. Whoops, what did I do there? Okay, what if I pick 2? Well, the absolute value of 2, if I plug that in, is just 2, right? And so this gets pretty boring now. Input of 2 gives me an output of 2. Input of 3 gives me an output of 3, etc. What about some negatives? If I input a negative 1, what's the absolute value of negative 1? Positive 1, yeah. So I get the point negative 1, positive 1. And if I keep going, right, if I input a negative 2, absolute value makes it positive, so the output is positive 2. So I go negative 2, positive 2, negative 3, positive 3. And we can see what we get here, right? We're just getting a V shape out of this, aren't we? There it is. So I get a V shape. Some key points are 0, 0, 1, 1, negative 1, negative 1 when we want to graph this thing. What's the domain? What's the set of all the possible x values the ant could stand on? Just type it in chat real quick for me. Or say it. Or somebody say it. That's even quicker. All reals, yeah, right? An ant, there's no x value, no x coordinate the ant couldn't stand on. What about the range, though? This time it's not all reals, is it? An ant cannot step on every possible y value, right? In fact, there is a lowest y value. There's kind of a bottom value there. What's the smallest y value that an ant could ever step on? 0, yeah. And then he could go up forever, though, couldn't he? So would everybody agree that the interval, if I want to write the range in interval notation, it's going to start at 0. That's my left endpoint, or my bottom endpoint in this case. And my top endpoint would be infinity. And I know I have to have parentheses with infinity because I forget there. What do I have to have next to the 0, though? Bracket or parentheses? Just type in B for bracket, P for parentheses. I need answers from everybody on this. Okay, that's better. Good. If I'm not getting answers from you, my assumption is you're not here today. Yeah, I got to have bracket, don't I? Because an ant could have a y value of 0. So that's my range. End behavior. Okay, it's as x goes as far to the right as possible. Well, that's infinity, right? An ant could go right forever. What is the function making him do in terms of his y value? As he goes to the right, he goes up, doesn't he? Forever. So as x approaches infinity, y approaches infinity. What if x approaches negative infinity? The ant could walk forever to the left. What's happening to his y values as he does that? What are they approaching? Just type it in chat. Yeah, positive infinity, right? As the ant goes left forever, it's also the function is taking it up forever. So positive infinity. And this is continuous too, isn't it? I could graph this without ever picking my pen off the board. Okay, so there's my absolute value parent function. Okay, moving on. Another one we want to look at is the quadratic parent function. The easiest quadratic is just f of x equals x squared. Well, let's make a t-table here to get some points on this thing. Well, what about right in the middle? We could do 0. If I input a 0, what's 0 squared? Everybody agrees 0 squared is just 0. 0 times 0 is 0. So we get a point at 0, 0. What if I input a 1? 1 squared, well, that's just 1, right? Input a 1, 1 squared is 1 for my output, so I get the point 1, 1. What if I input a 2? What's my output going to be in that function? Everybody type it in, please. If I input a 2 for my x, what is the function outputting for y? Yeah, outputting a 4. Good. Okay, so 2, 4. So on my parent function, when I input a 2, I output a 4, so I'm going over 2 and up 4. Okay, negatives. If I input a negative 1, what's my output? What's negative 1 squared? Everybody type it in, please. Yeah, it's positive, isn't it? Right? And there's a rule for that. If I square a negative number, the output is always positive, isn't it? In fact, if I take a negative number to any even-powered exponent, right? Any even exponent, 2, 4, 6, doesn't matter. I'm always going to get out a positive. So I have the point negative 1, 1. And then by that same thinking, if I input a negative 2 squared is positive 4. So I'm going to go back 2 and up 4. And so if I wanted to sort of connect the dots here in a smooth shape, this is one that's going to look like what we call a parabola. Instead of a V shape, it's a U-shaped graph. Okay, similar to an absolute value, but instead of a V, it's a U. So it looks so similar that a lot of this stuff is going to be the same. The characteristics are going to be really similar, aren't they? What's the domain here? What's the set of all possible x values the ant could stand on? Yeah, it's all reals, right? There's no limit to the x coordinates the ant could stand on. He could walk, if he goes far enough along this function to the right, he could go infinitely far. He could go infinitely far to the left also. But just like before, the range is limited. There is this bottom y value, which is 0 again, and then it goes up forever. So the range extends up to positive infinity. But there is a bottom y value, and we need a bracket there just like before because the ant could stand on the y value of 0. Okay. What about the end behavior? As x approaches infinity, well, if the ant goes to the right forever, the function is carrying him up forever. So as x approaches infinity, y or f of x approaches infinity. Fill in the blank for me on this one. Type it in chat, please. As x approaches negative infinity, what's f of x approaching? Type your answer in chat, please. Yeah, good. It's infinity, right? Because as the ant goes left forever, the function carries it up towards positive infinity in the y direction forever. And once again, this one I can graph without ever taking my pen off the board, so it is continuous. Okay, what about a cubic function? Well, that's very similar. Cubic just means, instead of quadratic, just means that now the power of x is a 3. So we're just going to get f of x equals x cubed. So we can make another t-table here. X, and instead of calling it y, we could call it f of x in our t-table. Doesn't matter. 0 cubed. If I cube something, I'm just multiplying it by itself a total of 3 times, right? So 0 times 0 times 0 is 0. So it goes through the point 0, 0. If I plug in a 1, well, what's 1 cubed in chat real quick? 1 times 1 times 1 is, or just show me fingers. What is that? Oh, yeah, it's just 1, isn't it? 1 times 1 times 1 is 1. So 1 cubed is 1. So again, it goes through the point 1, 1. Okay, what about this, though? What if I input a 2? What's 2 cubed? 2 times 2 times 2. Type it in chat. Yeah, it's 8. Okay, good. So it looks similar to our previous graph, only this one grows a little faster. It's a little more extreme. So if I want to put that point's actually off my graph. So if I go over 2, I got to go up 5, 6, 7. So right about there, maybe. There's the point, over 2, up 8. What about the negatives? What if I input a negative 1? What's negative 1 cubed? In other words, negative 1 times negative 1 times another negative 1. Yeah, it's negative 1, isn't it? Right? Okay, so we get a different result. If I take a negative number and I cube it, I'm getting a negative result out. In fact, it works for any odd exponent, right? If I take a negative number to any odd power, I always get a negative output. And then negative 2 cubed, negative 2 times negative 2 is 4, times another negative 2 would give me a negative 8. So I've got points over here at negative 1, and negative 2, negative 8. So there's 5, 6, 7. So right down about there maybe, huh? Negative 2, negative 8. And if I want to graph this one's going to look kind of like that, right? It's not a great graph, but you get the idea. Okay. What's the domain? Is there any ant value, any x value the ant couldn't step on? Another way of thinking about that is there any x value that I couldn't input into this function? No, there's not, right? I could input any positive or negative x value, right? There's no limit to the x values that I could input. I'm just going to input really big positive or negative y values after a while, right? But that's okay. Numbers go forever. So the domain is all reals. The range is pretty obviously all reals too, isn't it? The graph goes forever to the left and right and forever up and down. What about our end behavior? As x approaches infinity, so as the ant goes to the right forever, well, the graph is carrying him up forever, isn't it? So we get positive infinity for our output. As x approaches negative infinity, as the ant goes left forever, the graph carries him down forever. So y approaches negative infinity this time, right? And this one is continuous. Okay, give me 1 to 5 real quick before we move on this, how we're doing all this stuff. Okay, either flash me fingers or type a number in, please, everybody. Okay, all right, looking good. Moving on, let's look at some radicals, square roots and cube roots. How about? Okay, so the square root, the simplest square root function, our square root parent function, is f of x equals the square root of x. Okay, again, let's make a t-table with this. So what if I plug in 0 for x? What's the square root of 0? Just type it in. Yeah, 0, isn't it? Good. So I get the point 0, 0. Gotten that one every time so far, right? So 0, 0. Okay, if I plug in 1, what's the square root of 1? In other words, what number do I square to get 1? Well, 1, right? So it goes through 1, 1. Okay, what's the next convenient value? If I plug in 2, I'm not going to get back a very friendly answer. Square root of 2 is just, it's an irrational number, right? If I write it as a decimal, it never repeats, never terminates, 1.4142, blah, 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 forever. Square root of 3 doesn't work nicely. What's the first number I could input there and get a friendly integer output? 4. Yeah, the square root of 4 is 2, isn't it? Because 2 squared equals 4. Okay. So I input a 4, the square root of 4 is 2. So I go over 4 and up 2. And my graph's not very big, but the next one would be a 9, wouldn't it? I could input a 9 and the square root of 9 would be 3. So I'd go over 9 and up 3. How about negatives? What if I input a negative 1? What's the square root of negative 1? So that means what number could I square and get back a result of negative 1? What squared is negative 1? Ooh, I'm seeing some people with some quizzical looks there for good reason. Can you do it? Is there a number I could square and get an answer of negative 1? That doesn't work, does it? Right? Because if I square a negative number, I get a positive. If I square a positive, I get a positive. If I square 0, I get 0. Nowhere do I ever get back a negative answer if I square things, right? So that tells us something important. The square root of negative 1 is undefined. In fact, the answer, I can't ever put a negative number inside a square root. That's one of our 2 rules for real numbers. We've talked about one of them quite a bit. We can't divide by 0, right? But the other thing that we're just now coming upon is we can't take a square root of a negative number. In fact, we can't take any even root of a negative number. I can't take a square root, which is the same as a second root. I can't take a 4th root or a 6th root or a 100th root of a negative number. I never can input a negative number into an even root, in this case, a square root. And so there is no point at x equals negative 1. Our graph, in this case, does not extend to negative numbers. It starts at 0, 0 and just goes up from there. Okay? So it's a little different in that case. What's my domain this time? What's the set of all the x coordinates that the ant could stand on? It's not all reals this time, is it? There is a lowest x value, a smallest x value the ant could ever have. And what's that?
0.
Yeah, 0. So my domain starts at 0 and goes forever, right? So it goes to negative or to positive infinity. Do I include the 0? Do I need a bracket? B for bracket, P for parentheses here. Yeah, it's a bracket, isn't it? Because the ant could have an x value of 0. And so there's my domain. What about the range? Well, the range is really similar, isn't it? It starts at 0 and goes up forever. So it'd be bracket 0 infinity parentheses for my range. That looks terrible. End behavior. As x approaches infinity, as the ant goes to the right forever, the graph is carrying it up forever, right? So as x approaches infinity, y, or another way of saying it is f of x approaches infinity. What about at the other end? This time the ant can't approach negative infinity. What's the smallest, what's the left end behavior? The ant can only go how far to the left on this function? What's the furthest left he can go? So as x approaches, what value would be my furthest left? People are saying it's 0. Good. As x approaches 0, what y value does the ant approach? Well, it looks like as he's walking back along this function towards x equals 0, his y value is also 0. So there's my left end behavior. Okay. Now, what about this one? Is the function continuous? And think about our rule. Once I put my pen down, can I draw the entire graph without picking it up? If so, it's continuous. So give me a C or a D, continuous or discontinuous on this one. Just type it in chat. What do you think? Continuous or discontinuous? Okay, I'm getting a lot of C's. That's correct. It is continuous. It's a little weird, isn't it? Because it doesn't go forever, but once I put my pen down, I can graph the whole thing without ever picking it up again. So it is continuous. Okay, cube root. Let's look at a cube root. So cube root is similar. The way we write a cube root is I put a little 3 on the top of the radical. We call that the index of the radical to tell us it's a cube root instead of a square root. Okay, let's make a little t-table first of all. Whoops. Well, the cube root of 0, now we're answering the question, what could I cube to get 0? Well, that's 0, right? So we know we've got a point at 0, 0. What about if I input a 1? What cubed is 1? What's cube root of 1? Type it in real quick in chat. Yeah, it's 1. Good. 1 cubed is 1, so the cube root of 1 is 1. Okay, what's the next convenient one I could do? What's the next number I could input into, I could take a cube root of and get back a nice friendly integer answer. Cube root of 2, that's going to be some weird decimal, right? It's not even 4. What number could I cube and get 4? I don't know, some bizarre irrational number. What's the first number I could take a cube root of that's bigger than 1? Okay, people are suggesting 6. What about, 6 or 9? Those don't work, do they? Because what could I cube and get 6? I don't know. Right? What times itself again is 6? Nothing. And 9 doesn't work, but 8 does work, doesn't it? What's the cube root of 8? What could I multiply times itself and then multiply again times itself? Could I cube, in other words? Yeah, 2. 2 cubed is 8. So the cube root of 8 is 2. That one's off my graph. So I got to go over 8. There's 5, 6, 7, 8. And my output is a 2 for y. So it's got coordinates 8, 2. Okay, what about negatives now? What's a cube root of negative 1? Is there a number I could cube and get negative 1 as an answer? Type it in for me. Yeah, it's negative 1, isn't it? Now, I couldn't take a square root of a negative, but I can take a cube root. Negative 1 works, doesn't it? Let's check it. If I cube negative 1 times negative 1 is 1, times another negative 1 is negative 1. Yeah, it works. The cube root of negative 1 is negative 1. What's the next convenient one I could pick? Negative 8, wouldn't it? What could I cube and get a negative 8? A negative 2. So the cube root of negative 8 is negative 2. Once again, that's off my graph. So there's negative 5, 6, 7, 8. So there's the point with coordinates negative 8, negative 2. And then this graph, oh, whoops, I put that in the wrong, let me do that again. I put that in the wrong spot, didn't I? That one's supposed to be negative 8, negative 2, so it's right there. Let me try that again. Something like that. Okay, well, what's my domain? Well, there's no x value the ant couldn't step on, so that's all reals. And same with the y, right? I know this thing, it flattens out pretty quick, but if I go far enough to the right, I can go up as far as I want to. If I go far enough to the left, I can go down as far as I want to. So the domain of this, or sorry, the range is also all reals. End behavior as x approaches positive infinity. So if I go to the right forever, the function is going to carry me up forever also. So it's infinity. As x approaches negative infinity, as I go to the left forever, the function carries me down forever. So f of x approaches negative infinity, and it is continuous. Okay, next one's kind of a weird one. Reciprocal parent function. What's the reciprocal mean? It means I'm going to take the flip of any input value, right? So this one looks like if I input an x, the output is going to be the reciprocal. I'm going to flip that fraction, right? Let's make a t-table for this one. Okay, well, usually we start at 0. Okay, let's start at 0 here. What happens if I input a 0 for x? What's my output? What's my output? If I input, that's weird, isn't it? If I input a 0 for x, my output is 1 divided by 0. Can I do that? Can I divide by 0? I can't do that, right? Okay, so we know right away that at 0, I don't get an output, so that's undefined, right? There is no point at 0, 0, or at when x equals 0. There's no output, okay? Well, let's try the next one we could. What about 1? If I input a 1, what's the reciprocal of 1? 1, right? 1 is its own reciprocal. So it goes through the point over 1 up 1. What about some other points? What if I input 100? What's the reciprocal of 100? If I input an x value of 100, what's my output? What's it going to be? If I input a 100, what's the reciprocal of 100? 100 is the same as 100 over 1, right? So what's the reciprocal of 100 over 1? 1 over 100. Okay, that's small, right? 1 over 100 as a decimal is 0.01. That's really small, right? What if I input something really small? Like what if I input 1/100th? What's the output? What's the reciprocal of 1/100th? 100, yeah. So what's this telling me then? If I input a really big x value, the output is a really small y value. But if I input a really small positive x value, the output is a really big positive y value. That's creating a strange shape. That's creating a shape that does something like that. Isn't it strange? Small x input, big y output. Big x input, small y output. Okay, let's try some negatives. If I input a -1, what's the reciprocal of -1? If I flip -1, don't I just get -1? Right, so I've got a point over here at -1, -1. What if I input a really small negative number, like -1/1000th? What's my output going to be? What's the reciprocal of -1 over 1000? negative 1,000 over 1, which is negative 1,000. So in other words, if I input a really small negative number, the output is a really big negative number. What if I input a really big negative number like negative 1,000? Isn't the reciprocal of that going to be negative 1/1000th, which is the same as negative 0.001? Okay, so I'm getting similar behavior down here. This time it's going to look like that, though, isn't it? So that's the nature of my graph. Okay, let's look at that graph and let's see if we can come up with a domain in the range. Okay, what's the domain this time? Is it true that an ant could have any input value? Is there an x value the ant could not stand on? Look at our t-table. There's a single value that the ant can't stand on. What is that? 0. Yeah, it can't. X value can't be 0. And so our domain this time is everything except 0. That's the easiest way to write it. X can't equal 0. That implies that anything else is okay, but it can't be 0. Well, then is there a Y value if you look at this graph that the ant can never get to? Yeah, it's 0 again, isn't it? Y can also not equal 0. Okay, now these end behaviors are going to be a little strange this time. What's this end behavior here? As x approaches infinity, so as an ant walks as far to the right as possible, what's the y value or the f of x value, the output value that the function is approaching? This is going to hurt your brain a little bit, but this is interesting. This is when math kind of starts to this is an interesting topic. As x approaches infinity, so as the ant goes forever to the right, what y value does the ant approach? Yeah, I'm seeing it. I'm seeing some people answer 0. That's correct, right? F of x is approaching 0. Now, let me ask you this. Give me a yes or a no, just y or an n. Does the ant ever get to 0? Does his y value ever get to 0? Everybody answer this one, please. It never does. That's a strange concept. So something I do when I have students in class to help them understand this. So I'm going to talk you through this. You got to close your eyes, use your imagination here. So I'm standing about 2 meters in front of my door, facing my door in the classroom. Here's the game. I think I maybe mentioned this once before, but it's going to make more sense. If I mentioned this at the beginning of the year, it's going to make more sense now because it really applies in this situation. So what if I'm going to say that every second for the rest of eternity, each second I am going to take a step that is halfway to the door. So I'm starting 2 meters away. So after 1 second, I've now stepped halfway to the door. After 2 seconds, I'm going to take a shorter step and I step halfway to the door again. After 3 seconds, I take an even shorter step and I step halfway to the door again. Every second for the rest of eternity, I'm going to step halfway to the door. Do I ever get to the door? Yes or no? No, I don't get to the door, do I? Never get there. Okay, let me ask you this though. You know how when you buy Sharpies, you can have like a thick point on the Sharpie, or you can have a medium point or a fine point or an ultra fine point. Well, let's do an infinitely fine point on our Sharpie that we're going to buy from the Acme store here. Okay, if I have an infinitely fine pointed Sharpie, is there any point, like I'm starting 2 meters from the door, so between me and the door, is there any place on the floor where I could put a tiny little point with my infinitely fine point Sharpie that I won't eventually get to? Remember, every second I'm stepping halfway to the door. Is there any point that's not on the door? It has to be on the floor, right? It can't be on the door. Is there any point on the floor that I won't eventually get to when I'm stepping halfway to the door each second? Yes or no? Is there any point that I won't eventually step on? No, you're right. There is no point I won't eventually step on. And just to play devil's advocate here, what if I'm thinking, well, okay, what about this though? What if I just pick the point right next to the door? I eventually must step on that one, right? Well, is there a point right next to the door on the floor? There's not, is there? Because if I were just to zoom in on what I thought was the point next to the door, as I zoom in, I'm going to see that no, it's not. There's an infinite number of points still there if I zoom in far enough between me and the door always, right? There's no limit to the number of points between me and the door ever. So that's a weird catch-22. It's kind of seems like a paradox, doesn't it? That even though I never get to the door, there is no point that I could ever draw on the floor that I wouldn't eventually get to. Okay, so what we say then is, as time approaches infinity, what is the point that I'm approaching as in my my journey towards the door? As time approaches infinity, the point I'm approaching is the door itself, but I just never quite get there, right? Okay. So then, what if we go the other direction here? As x approaches negative infinity, if I go to the left forever, what's the value that I'm approaching? It's also 0, isn't it? Only they're negative values this time instead of positive values. Okay. So this is going to seem a little bizarre. Obviously, this function is discontinuous, isn't it? Right? I have to pick my pen off the board to graph this one. If I'm graphing this here, I'm going to go clear from negative infinity to the right and down forever. And then I got to pick my pen off the board and go and start up infinitely far up and draw the other part of this. Okay. You'll notice that this is a bizarre looking shape. But if I put a tack in the board right there at the origin, I could take this entire graph and I could spin it around 180 degrees and it would line up perfectly, wouldn't it? Right? So that's really what we call the point of rotational symmetry on this thing. If I put a tack there, I could just flip that whole XY plane. I could rotate it 180 degrees and it would look exactly the same. Okay. Well, there's a couple things. So discontinuous. There's something we could do to help graph this better. Okay, one thing I could do is I could put in some what we call asymptotes. Asymptotes, if I have to define an asymptote, here's what it is. I'm going to type this down here so it's you can read it better. An asymptote is a line at a function, or specifically the graph of a function, approaches but never gets to. Okay? That's what an asymptote is. If I graph some asymptotes on here, it makes it easier to see what's going on. There is a horizontal asymptote on this graph right there, isn't there? Let's put that right on the x-axis. Okay, there we go. There's a horizontal asymptote there. Oh, darn it. And there's also a vertical asymptote there. Okay, and what are the equations of those? Well, the horizontal asymptote is on the x-axis. The equation of that line is just the line. And I know the bell just rang. I'm going to get you out of here in just like 10 seconds. Whoops. That's the line y equals 0. So that's one of my asymptotes. The other one was the y-axis. Well, that's the line x equals 0. So those are my two asymptotes. I would say that, honestly, this is a little weird, but arguably the most important point for graphing this function is where those asymptotes meet. So it's the point 0, 0, even though it's not on the graph. Okay, think about that one. That's kind of weird, huh? All right, we'll leave off there. We'll finish this up next time. And then you guys the assignment's pretty simple. You're just studying these shapes of these graphs, just kind of memorization thing. All right, have a great day. I'll see you on Wednesday.